In the first couple of videos on quantum mechanics, maybe there wasn't anything that was too awfully strange to you, but now we're going to look at the wave nature of matter, which is where quantum mechanics starts to make predictions that classical physics would never have even imagined. So the idea of matter traveling in a wave-like nature was first proposed by a guy named Louis de Broglie. Some people will pronounce this de Broglie, but that's not how it's said. So it's French, but even in French it's kind of a weird name. It'd be pronounced de Broglie. Anyway, when he was a PhD student, as part of his thesis, he proposed that this equation that we saw for the momentum of a photon, I think we had it written in terms of momentum. Momentum of a photon was Planck's constant over wavelength. He said this is a universal equation that applies to everything, not just photons. It will also apply to matter waves. And if we rearrange this, so we kind of put the emphasis on the wave nature, so this applies to matter, which is a pretty strange idea. What the heck does it mean for matter to have a wavelength? And so all you need to do is divide Planck's constant by the momentum. Typically the momentum isn't all that small compared to Planck's constant, so the wavelength is going to come out to be really, really small, which is why we don't see this in everyday interactions, and we'll do a calculation of that shortly. But what this means is in certain situations you can get matter to act like a wave, and if you remember kind of the linchpin of the debate on whether or not light was a wave was the double slit experiment. So if we could get matter to go through double slits, could it possibly produce a double slit diffraction pattern, meaning the bright and dark fringe patterns that we studied when we were looking at light? And in fact, that is what we see. If we have here a gun that shoots out electrons, and then we have a couple of slits. Now mind you, these slits have to be much, much smaller than the slits to diffract light, because as you'll see in some calculations we'll do shortly, the wavelength of matter comes out to be very, very small. So these slits are even smaller, but if we shoot a beam of electrons at these double slits, so here's our electron beam, it goes through these slits, we get diffraction through these slits, and then on the screen, which is showing up here, if we hit copy screen, it kind of gives you an easier view of that, we get light spots and dark spots. Well, what does this mean to get light spots and dark spots on a screen from electrons? Well, you've just got a detector, and this is where the electrons are going to hit the detector. You'll get more electrons hitting here and here and here, and very few electrons hitting here and here. And this is kind of strange, because we thought electrons were particles, so how in the world are they behaving as waves? Well, we still don't have that question answered definitively, but we know that they certainly exhibit wave-like properties. And when these experiments were first done, they were actually first done shooting electrons through crystals, because crystals have a certain lattice structure that kind of behave like slits, and they were able to see the wave-like behavior, the diffraction of electrons through crystals. And some people said, well, maybe these electrons are kind of interacting with each other in a way that looks like a wave-like property, but they're just like pulling and pushing on each other. I guess they'd be pushing because they're negatively charged in some strange way. But then people figured out a more advanced experiment, I guess you could say, where they said, well, what if we shot these electrons one at a time? Okay, and again we're seeing this dual nature. So an electron goes through these slits. In order to go through these slits, it has to behave like a wave. But then when it registers at the detector, we get a single point being registered. And so I shoot another electron, I get another single point, I get another single point, and we can click rapid here and they will go faster. And even if we do this for a while, it's going to take a long, long time before we will have enough electrons to see this pattern. So let's skip doing that and jump back to our slideshow. So here is what we see when we let that experiment go for a while. This was actually not fully done with the double slit experiment until 1982. A guy named Akira Tanemura, who was working at Hitachi, the same Hitachi that makes hard drives and other electronic stuff, I'm sure. He actually performed the double slit experiment with electrons. We were able to see it before in other types of diffraction situations, like I mentioned earlier with crystals. So he let this run for about 20 minutes, shooting about 10 electrons per second, which was slow enough that they were going one by one. They weren't interfering with each other. And we end up, if you look at this guy here, with a diffraction pattern. Light fringes and dark fringes. This is essentially where more electrons ended up hitting. And to me, this really, shines a light on the strange wave-particle duality of both light and matter waves. So in order to go through the slits, it behaves like a wave, then it hits the detector like a particle, but then the collective, the aggregate of all of these particles hitting reveals a wave-like pattern. So what is going on here? We don't really know. Similar to what I discussed with light, we don't know exactly what an electron is, whether it's a wave or a particle, or sometimes one or sometimes the other. We just have a number of observations that correspond to what we typically think of as wave-like behavior or particle-like behavior. And similar to the light experiments, if we shoot these electrons and we block one of the slits, then we don't get this pattern at all. We just get a whole bunch of electrons hitting behind that one slit. So you have to have these two slits, and each individual electron in some way is passing through both slits. I know that's kind of weird, but that's amazing. Quantum mechanics tells us that the way we think about how nature works is not really accurate on the fundamental level. An electron can pass through two slits and then behave like a wave as it does so, and then hit a detector and behave like a particle. Okay, let's do a couple calculations. So if we want to find the de Broglie wavelength of a 100-mile-an-hour fastball, so this is like the professional baseball player, and given this mass of the baseball, what is the wavelength? So our de Broglie wavelength is Planck's constant over momentum. And if it's a particle, we can just use the regular, or not even a particle, I mean if it's a matter wave, we can use the regular expression for momentum for matter. So we can have h over mv, just our regular equation for momentum. Now, if it is moving near the speed of light, we do need gamma mv, we do need the relativistic momentum, but a baseball at 100 miles per hour is not anywhere near relativistic speed. So we plug in Planck's constant, 6.6 times 10 to the negative 34th, and then we divide by the mass of the baseball, 0.145, times the velocity of the baseball. We want SI units, so don't use that 100 mile per hour thing, 44.7. This works out to be 1.0 times 10 to the negative 34th meters. Okay, this is an incredibly small number. So again, this is why we don't notice the wave-like nature of ordinary objects. This is why the baseball doesn't diffract around the bat, because the bat is much larger than 10 to the negative 34th meter, and you need a barrier or a slit on the order of magnitude of the wavelength in order to see those wave-like properties. Now let's look at an electron, on the other hand. And let's say we have an electron that's got a kinetic energy of 100 electron volts. So we're going to use the same equation. We're going to use lambda equals Planck's constant over mv. But we're going to have to do a little extra calculation to get the velocity of the electron given its energy. And on top of that, we have to convert the energy to joules before we can set it equal to 1/2 mv squared. So the conversion between electron volts and joules is 1.6 times 10 to the negative 19th times 10 to the negative 19th joules per electron volt. So this is easy. We just knock a couple numbers off of our exponent here, and so 1.6 times 10 to the negative 17th joules of energy. So we can set that equal to 1/2 mv squared, the kinetic energy, and we can solve for velocity. So velocity is going to be 1.6 times 10 to the negative 17th. The 2 comes up over here, and then we divide by the mass. The mass of an electron is 9.1 times 10 to the negative 31st kilograms. We're going to square root that whole thing because this one was squared. and we get a velocity of 5.9 times 10 to the 6th meters per second. So even in this case, it's going much faster than the baseball was, but it's still 100 times less than the speed of light, over 100 times less, so we don't have to worry about relativistic stuff. And I don't think I'll give you any homework problems where you do, because that was a separate unit and we're not going to worry about it for now. Alright, so again, plugging in Planck's constant, 6.6 times 10 to the negative 34th, divided by the mass of the electron again, 9.1 times 10 to the negative 31st, times this velocity of the electron. And just as we suspect, we're going to get a much shorter wavelength than we did for the baseball. We get approximately 1.2 times 10 to the negative 10th. Now that's still a pretty small wavelength, but compared to the wavelength of the baseball, this is much, much larger. And basically what's going on is we have very small masses, even though our speed is quite large. If we have a very small mass, it's going to be a lot easier to see these wave-like properties. And we've seen wave-like properties for protons, for neutrons, which are much more massive than electron. We've even seen it for helium nuclei. We've been able to do this with alpha particles. So there you go. Even when you are running down the street, you have a wavelength. So enjoy. See you next time.